Funding for this program was provided by the Annenberg CPB Project.
Force equals mass times acceleration. Mechanics, the science of motion, can be summarized in that one equation, F equals ma. It is the heart of classical mechanics.
In 1543, Copernicus wrote this little book, and the Aristotelian world started to come unglued. 150 years later, it still lay in ruins, and there was nothing to take its place. Of course, some progress had been made. Kepler had discovered his 3 laws, falling bodies were understood, and so was inertia. But there was no unifying principle. The seamless perfection of the Aristotelian world had turned to buzzing confusion. And then, in one breathtaking book, Isaac Newton invented physics as we know it today and restored order to the heavens and the earth.
When trying to describe the basic machinery of the world, a natural question is, where to begin? Isaac Newton began with 3 fundamental principles, Newton's laws, and with the incredible speed and elegance of unleashed genius, he explained the motion of almost everything on and above the surface of the earth. Refined to their essence, Newton's 3 laws are one profoundly powerful equation. Force equals mass times acceleration. Understand that equation, what it means and how to use it, and in the end, it's possible to understand the mechanical universe. At the same time, understand that considerable complexity can reside in what appears to be pure and simple. For example, a closer look at F equals ma immediately reveals 2 complications. First, F equals ma is a vector equation. Both force and acceleration are vectors. In other words, they have definite directions. In F equals ma, they must have the same direction. The second complication arises in the symbol A for acceleration. Remember, acceleration isn't the position of something, and it's not how fast something changes its position. Acceleration is how fast something gets faster. So, acceleration is the derivative of a derivative. And Isaac Newton's simple equation, F equals ma, is a vector equation about a derivative of a derivative. For example, when a body or mass falls, gravity exerts a force, F, force in the downward direction, of course, and the result is acceleration. So there it is. F equals ma. Acceleration and force in the same direction. Complicated yet beautiful in its simplicity. That's the well-known equation. Now, in the case of a falling body, what's known about acceleration? It's constant, for one thing, and for another, it's the same for all falling bodies. And what's more, it's called G. The force of gravity on every falling body equals its mass times the acceleration, G, in the downward direction. But this equation also describes motion for other than the downward direction. Gravity exerts the same force on a body no matter which direction that body travels. Once an object's in motion, aside from air resistance, gravity is the only force acting on it. Whether dropped from a tower, shot from a towering mountain, or heaved by a towering mountain of a man.
Measure.
All moving objects fall under the influence of gravity. An equation that explains the path of any projectile on Earth is powerful indeed. And to see how it really works, it's necessary to go back to the beginning. With his first law, Newton embraced the idea of inertia. He wrote, "Every body continues in its state of rest, or of uniform motion in a straight line, unless it is compelled to change that state by forces impressed upon it." Inertia was an idea that Newton inherited from Galileo. It was an extraordinary idea that, if illustrated with modern images, goes something along these lines. Once a body is in motion, it naturally continues in a straight line unless influenced by some force. Newton's second law indicates exactly how force changes the motion of an object. As Newton himself explained it, the change in motion is proportional to the force impressed, and it is made in the direction of the straight line in which the force is impressed. Newton used the word motion to mean momentum, the velocity of a body multiplied by its mass. While Newton expressed himself with classical geometry using geometric figures and ratios between quantities, he knew his laws could be expressed as differential equations.
Newton's second law says that the impressed force is equal to the rate of change of momentum. For a body with constant mass, this differential equation reduces to force equals mass times acceleration, F equals ma.
To every action, there is always an equal reaction. Or, the mutual actions of two bodies upon each other are always equal and directed to contrary parts. This is Newton's third law. Something cannot touch something else without being touched in return. In other words, bodies don't merely act, they interact with one another. At the same time, all three of Newton's laws act and interact throughout the physical world. And the trajectory of any projectile in a powerful and moving fashion demonstrates the consequences of Newton's three laws. When an object is launched, then allowed to travel freely, what's the nature of its trajectory? No matter what the projectile and its purpose, could it be that all trajectories are essentially the same? Understanding the course of any projectile arises from an insight into the laws that govern force and motion. One young fellow credited early on with such an insight and first-hand knowledge about projectiles was David, who's remembered for his legendary confrontation with Goliath. Against considerable odds, young David demonstrated the relationship between force and momentum. Actually, David and Goliath might not have been quite as mismatched as legend portrays them. After all, is this the model of devastating intellect? In any case, David managed to demonstrate force and momentum expertly, and without the help of Aristotle, much less Newton. And Goliath got the point. Not only that, he routinely obeyed the law of gravity, another phenomenon that worked perfectly well long before it was understood. Newton's laws did not change the way the world works, but they changed forever the way in which it's understood. And whether it's on a field of battle, an athletic field, or the green fields of England, the path of any projectile can be described in the field of mathematics. In Newton's own words, then from these forces, I deduce the motions of the planets, the comets, the moon, and the sea. Newton wasn't the first to ponder the path of a flying object on Earth, or that of one in the heavens. But he stood alone in his knowledge that the same laws govern the course of both. Still, long before Newton, Galileo Galilei described projectile motion perfectly. He realized bodies can fall vertically and move horizontally at the same time. From Galileo's point of view, which took in everything from the heavens to the heavenly gardens of the Renaissance, a body's motion has two components, completely independent of each other. Galileo's extraordinary vision is explained by Isaac Newton's extraordinary equation.
The vertical component of the vector force is mg downward, or minus mg. No force at all acts in the horizontal direction. Only the vertical component of acceleration is minus g. In the horizontal direction, where there is no force, the acceleration is 0. Acceleration is the rate of change of speed. Since the horizontal speed is not changing, it must be constant. Constant speed in the horizontal direction and constant acceleration downward, both acting independently and simultaneously.
These are the elements of Galileo's trajectories. And they're also the results of Newton's equation. Force equals mass times acceleration. F equals ma. But to understand the ongoing significance of F equals ma, it's necessary to return to a time before scholars had its help in grappling with worldly phenomena. In ancient Greece, scholars believed that everything in nature came to rest, that coming to rest was the nature of all moving things. According to the Aristotelians, all moving objects were propelled by a mover. When the mover couldn't be seen, as in the case of projectile motion, Aristotle said that air itself was responsible for the movement. Much later, even though Europe in the Middle Ages retained the Aristotelian worldview, that explanation wasn't entirely satisfactory. To explain the unescorted motion of projectiles, such as spears, arrows, and cannonballs, scholars came up with the idea of impetus. Launching a projectile imbued it with a finite amount of impetus, which gave the object its motion. When its impetus was consumed, the object suddenly dropped to Earth. Impetus wasn't a bad idea, but it fell short of its target. The medieval idea of impetus fell just short of the principle of inertia, which wasn't hit upon until the Renaissance, when the parabolic path of a real projectile was discovered by Galileo. In Galileo's words, "It has been observed that missiles and projectiles describe a curved path of some sort. However, no one has pointed out the fact that this path is a parabola." With such insight, Galileo was living to see the 2,000-year reign of the Aristotelian worldview come to an end. And he wasn't alone. About the same time, Johannes Kepler, Christian Huygens in the Netherlands, and René Descartes in France, and others also began to see the universe with new eyes. As extraordinary as this collection of scientists was, their individual viewpoints overlooked something: a synthesis, an organizing principle for the physical world as a whole. It would take extraordinary circumstances to explain the world. It would require the right person in the right place at the right time. The right time was 1665. And the right person was Isaac Newton. At only 23 years of age, Newton conceived the discoveries that would alter forever the world's understanding of the universe. With just 3 fundamental laws, Newton gave motion a cause, and in doing so, his dynamic principle completed Galileo's mathematical description of motion. In other words, while Galileo's kinematics describe motion, Newton's dynamics explain it. But Newton's laws also explain how a body moves. By combining his calculus with his mechanics, the motion of a moving object can be described perfectly.
To go to right.
The motion of a projectile has an acceleration equal to -g in the vertical direction and a constant speed in the horizontal direction.
And what's the meaning of that constant? The force behind this object's propulsion comes from the thrust of the athlete's torso. This force lasts only for a moment and determines the shot's initial speed. When the shot leaves the hand, it has some component of velocity in the x direction, which is the constant value the horizontal speed has, and will continue to have throughout its journey until it hits the ground. However, the vertical component of velocity is changing at a rate equal to -g. The derivative of vertical speed with respect to time is -g, not 0. What function has the derivative -g? Minus gt is one answer. But minus gt plus any constant is also an answer, since the derivative of a constant is 0. What's the meaning of the constant? It's the vertical speed the object starts out with, even if it starts out with a bang. Pretend for a moment that there is no gravity. Then, any projectile would follow a straight line path with both the horizontal and the vertical speed with which it started out. But gravity does shape the motion of a projectile. And how it does is expressed in Galileo's law of falling bodies. What really happens is that a projectile continually falls beneath its imaginary straight line path at a rate equal to 1/2 gt squared, just as if it were dropped from rest. All these hard-earned insights of Galileo are the simple and direct consequences of Isaac Newton's one concise law, summarized in the equation F equals ma.
I've got another David and Goliath story for you. Naturally, I'm David, and there's Goliath hanging from a tree. But this time, instead of a sling, I'm going to get him with a sophisticated projectile. This one. Now, there's just one problem. I know that at the moment that I pull the trigger, he's going to be frightened and let go of the tree he's in. And so he's going to be falling. And the question is, where do I aim in order to hit him while he falls? How much do I have to lead him by in order to hit him? Well, I'm going to find the answer the way any great hunter would. I'm going to write the equations of the projectile. What we need to know is z and x. And what we know instead is dz dt, because that's just vz, equal to minus gt plus vz naught, and dx dt, because that's just vx, equal to vx naught. Minus 1/2 gt squared. Now, without the effect of gravity, these would be the equations of a straight line. It would be a straight line directly from the barrel of the gun to the point that it's aimed at. The effect of gravity is to make the missile fall below that straight line by an amount equal to 1/2 gt squared. So the actual trajectory looks like that. But that's exactly the same distance that the monkey will fall, provided the gun was aimed directly at the monkey in the first place. He'll fall just the same, 1/2 gt squared, and meet the missile in midair. And so that's what we want to do. That's the solution to the problem. We want to aim the missile directly at the monkey. And that's what I'm going to do. Now I'm going to shoot down that monkey. Now, someone is bound to ask me why I would shoot a monkey. Don't ask. This is not a course in ethics, it's a course in physics. Now you can see that the laser beam passes by the sights of the gun. There's one sight, and there's the other sight, and it hits the monkey. So the gun is aimed directly at the monkey. Now I'm going to load up my missile launcher here, and now we're ready to shoot him. Okay, I have to tell you that I have practiced this demonstration many, many times, and in all the hundreds of times that I've done this demonstration, I have never once hit that monkey. That's why he keeps volunteering for this job. Okay, we're going to do it now. Everybody ready? Here we go. Ah! We got him. That may be the first time a monkey has ever been shot down by an equation. But what an equation it is. If you ask the average physicist in the street what is the most important single equation in all of physics, this is probably what you'd get. F equals ma. And yet, there's something very mysterious about that equation. It has just three quantities in it: force, mass, and acceleration. By now, we pretty well understand what acceleration means. But what exactly is force? And for that matter, what do we mean by mass? One way to find out is to use this equation to tell us. That's what we've pretty well done today in the case of gravity. We found out nothing about the nature of gravity or why it works the way it does, but we use this equation to tell us the force acting on a body. It told us nothing at all about gravity or how it works. If we know the mass of a body and we observe its acceleration, we can find the force on it. But without this equation, we don't know the mass of a body. And without knowing the mass of the body, the equation means nothing at all. Is it possible that the most important single equation in all of physics is a meaningless logical absurdity? I'm not just playing with words. This is a problem that philosophers have debated for over 300 years. And yet one thing is very clear. Before Isaac Newton wrote this equation down, the world was a world of buzzing confusion. And after he wrote it down, the world became orderly, comprehensible, and predictable. So whatever else this equation is, it certainly isn't meaningless. The only way to understand what this equation is about is by using it. And that's what the rest of our story is about.
Force equals mass times acceleration. Mechanics, the science of motion, can be summarized in that one equation, F equals ma.
Funding for this program was provided by the Annenberg CPB Project.